Hello there, and welcome to Calm Science for Sleep, where the universe is explained slowly enough to fall asleep to, and nothing is ever in a hurry. Tonight, we're going to ask one question, and we're going to take our time with it. How big is the universe, really? But before we go anywhere at all, I want to give you something to hold. Right now, you are moving at about 1,000 miles an hour. Not in a car, not on a plane, lying exactly where you are. That's the speed the Earth is turning underneath you, and it hasn't stopped once in your entire life. You're also going around the sun at 67,000 miles an hour. That's about 18 miles every second. In the time it took me to say that sentence, you traveled further than most people drive in a week. And the sun is carrying you around the center of the galaxy at 500,000 miles an hour. 3 enormous motions, stacked on top of each other, all happening to your body at this moment. And you can't feel a single one of them. No wind, no lurch, nothing. Because everything around you is moving with you, the bed, the room, the air in your lungs. That's the first thing worth knowing tonight, and everything else will rhyme with it. The biggest things are almost always the ones you cannot feel. I should say at the start, no one has ever really answered that question in a way the mind can hold. You can write the number down. You can say it out loud. But actually feeling what it means, that always seems to leave the imagination overflowing, no matter how carefully it's explained. So I'm not going to promise you'll understand it by the end. What I can promise is that you'll have walked the whole way there, one honest step at a time, and that somewhere along the walk, you'll almost certainly be asleep. Before we set off, where in the world are you listening from this evening? Let your breathing slow a little here. Nothing tonight needs to be understood quickly. Perhaps a city where the streetlights have washed the stars out and you haven't seen the Milky Way in years. Perhaps somewhere quiet where you could step outside right now and see more than you could count. Or perhaps it's very late and the house has finally gone silent. Wherever you are and however your day has been, you're in the right place now. If these slow journeys help you rest, tapping subscribe quietly helps someone else find their way here too. Someone lying awake tonight who needs a calm voice to drift along with. That's the only reason I mention it, and I won't bring it up again until the very end. Now, take a breath. A slow one, in through the nose and out through the mouth. Let your shoulders drop away from your ears. Let your hands rest wherever they've fallen. If your eyes are already closed, that's perfectly fine. There's nothing to watch tonight. You only need to listen. Let your body settle. This is a slow journey, and you are allowed to sleep through most of it. Here's how tonight will go. We're going to climb. That's the honest word for it. We start with something you can hold in your hand, and every step will be so much larger than the last that the last one seems to vanish. 19 times. Then we look back down the whole staircase at once. And one thing about the word before we set off, because it matters. Big can mean how far across a thing is, the kind you could measure with a very long tape. But it can also mean how long it takes to cross, and that's where it gets strange, because out there, distance and time turn out to be the same measurement, wearing different clothes. There's a third meaning too, and it's the one we'll arrive at last: how much of it you're allowed to see at all. That sounds philosophical. It isn't. It's a physical limit, and it has a number. Now, let your shoulders drop one more time. Let your breathing slow. Let's begin with the ground you're lying on and see how far it gets us. We ended by noticing that you're already moving without feeling it. So the natural place to start is the thing doing the carrying, the world underneath you. The Earth is a sphere about 7,900 miles across, a little under 13,000 kilometers. Around the middle, its circumference comes to just under 25,000 miles. Say that slowly. 25,000 miles. It's a number you can almost hold because people have actually crossed it with their bodies. If you could walk without ever stopping, no sleep, no meals, no oceans in the way, at an ordinary strolling pace, walking right around the world would take you a little under a year of continuous walking. Not a lifetime. A year. And people have done something close to it. They've walked and sailed and ferried their way around the whole planet and come home again with sunburn and blisters and ordinary stories about the weather. The Earth is large, but it's a human. Kind of large. It is the biggest thing our feet have ever properly measured. And here's the part that I think deserves more attention than it usually gets. We have known that number for over 2,000 years. Around 240 BC, a librarian in Egypt named Eratosthenes worked it out. According to the account that has come down to us, he had heard that at noon on the summer solstice, in a town far to the south, the sun stood directly overhead and cast almost no shadow. In his own city, on the same day, at the same hour, a vertical stick did cast one. That's the entire experiment. A well, a stick, and one afternoon. If the Earth were flat, both would have no shadow, or both the same shadow. The fact that they differed meant the surface was curved, and the angle of that one shadow, combined with the distance between the two towns, gave him the curve, which gives you the circumference of the whole world. His answer came remarkably close to the modern figure. How close depends on which ancient unit of length he was using, and that is still argued over. But it was the right size by a very long way. A man with no telescope, no photograph, no way of getting more than a few hundred miles from home, measured the size of the planet using a shadow and some careful thinking. Nearly 2,000 years before anyone sailed around it to check. Rest softly here for a moment before we go on. I mention this now because it sets the tone for everything ahead. Every enormous number tonight was reached the same way, not by going there, but by noticing something small and being extremely careful about what it implied. Now, let me give you the ruler we'll use for the rest of the night, because miles are about to stop being useful. Light travels about 186,000 miles every second. That number means nothing on its own, so here it is, in a shape you can picture. In one single second, a beam of light could go around the Earth's equator 7.5 times. 7.5 laps of the entire world. In the time it takes to say the word second. So here is our world, measured in light. The whole Earth, edge to edge, is a little under a 20th of a light second wide. Hold on to that. From here on, light is our tape measure, and we'll watch that measurement grow all night. There's one more thing about this world before we leave it, and it's the part that catches people off guard. The air you're breathing right now is not an ocean. It's a film. Breathe out gently. Let the ground under you be quiet for a moment. Almost all of the atmosphere, the part that holds weather and birds and clouds, and every breath any creature has ever taken, sits within about 10 miles of the surface. Above that, it thins away to nearly nothing, very quickly indeed. 10 miles. If you shrank the Earth down to the size of an apple sitting on your kitchen table, the entire breathable atmosphere would be thinner than the apple's skin. Everything that has ever lived, as far as anyone knows, has lived inside that skin. Every forest, every city, every conversation anyone has ever had. The same is true going the other way, downward. The deepest point in any ocean is about 7 miles. The highest mountain is about 5.5. Put them together, and the entire vertical range of the Earth's surface, from the bottom of the Mariana Trench to the summit of Everest, is roughly 12.5 miles. On a globe the size of an apple, that whole range would be shallower than the texture of the skin. If you ran your thumb over it, you would feel nothing. Everest would not register. The deepest trench in the world would not register. Every mountain that has ever been climbed, every valley anyone has ever walked into, the whole vertical drama of the planet, smooth to the touch. A billiard ball manufactured to the same tolerances would be considered rather rough. It isn't quite a sphere either, and the reason is the spinning we started with. Because the Earth turns, the material at the equator is flung outward very slightly, not enough to notice, but enough to measure. The planet bulges around the middle by about 13 miles compared with pole to pole. It is very slightly squashed, like a ball of dough spun on a fingertip, which has a consequence I like very much. You weigh less at the equator than at the poles. Only a fraction of a percent, a person of average weight, would be a few ounces lighter standing in Ecuador than in Norway. But it is genuinely true, and it happens for 2 reasons at once. You're further from the center of the planet, so gravity has slightly further to reach. And you're being flung outward by the spin, which cancels a tiny amount of your weight. Let your hands rest where they are. There is no rush at all in any of this. The highest point above the Earth's center isn't Everest either. Because of that equatorial bulge, a mountain in Ecuador, called Chimborazo, much shorter than Everest by ordinary measurement, has a summit that sits further from the center of the planet than any other point on the surface. So, the top of the world depends entirely on what you're measuring from. From sea level, it's Everest. From the middle of the Earth, it's a mountain most people have never heard of. That's the last thing I'll say about our planet, and it's a fair warning for the rest of the night. Almost every biggest and furthest in astronomy comes with a hidden phrase attached: measured from where and measured how. Tonight, I'll try to keep telling you which one we're using. I don't tell you that to make it sound fragile, though it is. I tell you because it's the first honest hint of the shape of the whole night. The things that matter most to us usually turn out to be much thinner and much smaller than we imagine, and they are surrounded by a truly enormous amount of quiet, empty space. So when we ask how big the Earth is, we now have 3 answers, and they're all the same answer in different clothes. It's 25,000 miles around, about a year of walking. It's a little under a 20th of a light second wide, and it's wrapped in a layer of breathable air 10 miles deep, which is the only part of it any of us have ever actually used. That's step 1 of 19. It is the largest thing we will meet tonight that still feels ordinary. And here's the thing that makes the next step worth taking. The nearest object to this world, the one you can see out of the window most nights, the one that looks close enough to be part of the scenery, is far enough away that every single planet in the solar system could be lined up in the gap between here and there. All 7 of them, side by side, with room left over. Let's go and stand in that gap. Let your breathing settle here, slowly and softly. There is nothing to hold on to and nothing to remember. Just let the quiet world underneath you be that size while you rest. When we finished with the Earth, we left it as a ball 25,000 miles around, wrapped in a skin of air. Which makes the next question almost automatic. How far away is the nearest thing to it? The Moon sits about 239,000 miles away. That's roughly 10 trips around the Earth, laid end to end in a straight line pointing away from us. Think about that as a piece of walking. We said 1 lap of the world is about a year of continuous walking. So the distance to the Moon, on foot, would be about 10 years of walking, if there were anything at all to walk on. And here is the fact that never quite loses its strangeness, the one I promised you at the end of the last step. Every planet in our solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all 7 of them side by side, edge to edge, would fit into the gap between the Earth and the Moon. With a few thousand miles to spare. The gap looks small in pictures. In almost every drawing you have ever seen, the Moon hangs close by, like a lamp above a table. That's not because anyone is lying. It's because, if you drew it to scale on a page, the Earth would be a small marble at the left edge, the Moon a grain of rice at the right edge, and the entire middle of the page would be blank. That blankness is the real subject of tonight, not the objects. The space between them, measured in light, the moon is about 1 1/3 seconds away. Which means that when you look up at a full moon, you are not seeing it as it is. You are seeing it as it was a moment and a bit ago. The light left, crossed all that emptiness, and arrived at your eye slightly late. It's a tiny delay, barely longer than a heartbeat. But it is the first time tonight that we meet an idea which will follow us all the way to the top of the staircase, getting larger at every step. Looking out into space is looking backwards in time. Always. Without exception. The further away a thing is, the older the news. Take a slow breath here. Let the quiet of that place settle around you. The moon's news is 1 1/3 seconds old. That is the freshest news in the entire sky. There's one more thing about that distance that almost nobody knows, and it's my favorite small fact in the solar system. The moon is leaving. It drifts away from us by about 1.5 inches every year, roughly the rate your fingernails grow. It's been doing that for 4.5 billion years, which means it used to be very much closer, and the tides used to be enormous, and the days used to be shorter. And it means something else, which is genuinely lucky. Right now, by pure coincidence, the moon appears in our sky at almost exactly the same size as the sun. The sun is about 400 times wider, and also about 400 times further away. Those two numbers cancel. That coincidence is the only reason total solar eclipses exist. The moon covers the sun's disk almost perfectly, leaving just the corona visible around the edge. It has not always been true, and it will not always be true. Far enough in the past, the moon was too close and covered too much. Far enough in the future, it will be too far away and will never quite cover it again. The eclipses will all become annular, a ring of light with no corona, and the last total eclipse will happen without anyone knowing it was the last. We happen to be alive during the window when it works. There is no reason for that. It's simply the era we arrived in. 12 people have stood on that surface. The journey took them about 3 days each way, in a craft not much roomier than a small car, and they came back with dust in the seams of their gloves that still smells faintly of gunpowder. 3 days. That is the furthest any human being has ever traveled from home. And I want to be clear about what that means for the rest of tonight. In every single step we take from here on, no person has ever gone. Not close. Not a fraction of the way. Let your shoulders soften. Nothing out there is asking anything of you tonight. I find something restful in that, rather than sad. It means the rest of this journey is one we take only with our minds, and minds travel very lightly indeed. No fuel. No water. No air to carry. No return trip to plan. So when we ask how far away the moon is, the answer comes in 3 shapes now. It's 239,000 miles, 10 laps of the world laid end to end. It's wide enough to swallow every planet we have. And it's 1 1/3 seconds of light, which makes it the most recent thing you will ever see in the night sky. Notice what just happened. The distance to the moon is about 25 times the width of the Earth itself. Our first step didn't add. It multiplied. Every step from here will do the same, and that's why the numbers get away from us so quickly. We aren't climbing a ladder with even rungs. We're climbing something where each step swallows the whole of the last one. The next step swallows the moon 400 times over. And it's the one thing in the sky you've been told never to look at directly. Take a slow, gentle breath now. Let your body rest a little heavier against the bed. The moon has been drifting quietly away all along, and it asks nothing of you tonight. The moon left us with a distance we could still walk, if only there were ground. The sun takes that away for good. It sits about 93 million miles from where you're lying. We've gone from hundreds of thousands to tens of millions in a single step. That's roughly 400 times further than the moon. And because 93 million is an awkward thing to carry around, astronomers gave it a name and turned it into a ruler. That distance, Earth to Sun, is called 1 astronomical unit. 1 AU. For the next stretch of the climb, everything gets measured in those. Earth sits at 1. That's our new tape measure, and it's a good one, because for a while, everything ahead can be described as a small handful of them. In light, the sun is about 8 minutes and 20 seconds away. That's the second time delay of the evening, and it's a far more personal one than the moon's. Sunlight is 8 minutes old when it touches your skin. The warmth you felt on your face the last time you stood outside in the afternoon had already left its source before you'd finished the thought you were having. The sun itself is about 865,000 miles across. 109 Earths would fit side by side across its face. If it were hollow, you could pour something like 1,000,000 Earths inside it and still have room to shake the jar. Which brings me to the number that reframes everything. The sun contains around 99.8% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, all of it added together, is the rounding error left over after the sun was made. Imagine the entire solar system as a large glass jar of sand sitting on a shelf. The sun is the sand. All of it. The planets are a few grains you'd need tweezers and very good light to pick out. We tend to talk about the solar system as a family of worlds, with the sun as a sort of fireplace in the middle. It's more honest to say it's one star, with some dust in orbit, and we happen to live on a speck of that dust, and it is by far the most interesting thing in the jar to us, and that is entirely all right. Breathe slowly. Let the warmth rest on you. Before we leave, one more thing about that 8-minute journey, because the light in your eyes tonight is far, far older than 8 minutes. Sunlight is made in the core, where the pressure and temperature are high enough to fuse hydrogen into helium. But the sun is not transparent. A photon born in the core doesn't fly out. It gets absorbed almost immediately by the dense plasma around it, re-emitted in a random direction, absorbed again, re-emitted again, millions upon millions of times, staggering outward in a drunken walk that gets it a fraction of an inch further with each step. Estimates for how long that takes vary enormously, but they are all measured in tens of thousands of years. Some run to 100,000, which means the energy warming your face on a summer afternoon was made in the sun's core, while the last ice age was still ahead of us. It spent that entire time trying to get out. The 8 minutes across open space were the easy part, the last, quick sprint at the end of a journey that took longer than human civilization has existed. Breathe slowly now. Let the warmth of that thought stay with you. The sun is also losing weight while it does this. About 4 million tons of it become light every second. It has been doing that for 4.5 billion years, and it has enough left for roughly 5 billion more. And there's a problem with the sun that nobody has fully solved, which I find rather cheering. The surface is about 10,000 degrees Fahrenheit. Hot, but comprehensible. Above the surface, though, out in the thin outer atmosphere, the corona you see as a pale halo during a total eclipse, the temperature is closer to 2 million degrees. 200 times hotter, further from the source of the heat. That is not how fires work. Move away from a campfire and it gets cooler. Every instinct you have about heat says the corona should be the coolest part, and instead, it is by far the hottest thing in the solar system. We have candidates for why. Tangled magnetic fields snapping and reconnecting. Waves carrying energy up from below. Countless tiny flares, too small to see individually. A spacecraft is currently flying through the corona itself, repeatedly, to find out, and it has narrowed things down without closing the case. So the star we orbit, the most studied object in the sky, the one we can watch continuously, the one whose light we have been measuring for centuries, still has a basic fact about it that nobody can fully explain. I mention it on a night about size for a specific reason. It is easy to hear 3 hours of confident numbers and conclude that all the questions are answered and only the distances remain. They aren't. There is an unsolved problem 93 million miles away, sitting in plain sight on the object we understand best. The universe is not mostly settled with a few gaps. It's mostly open, with a few settled parts we happen to be standing on. There's one more thing about the sun worth carrying into sleep, and it's the most generous fact in this chapter. It is an ordinary star. Genuinely, unremarkably ordinary. Not the biggest, not the smallest, not unusually hot or old or strange. If you gathered every star in our galaxy and lined them up by size, our sun would stand somewhere in the middle of the crowd, difficult to pick out. Let your eyes stay closed. The light will keep arriving, whether you watch it or not. The thing that gives us light and warmth and weather and every crop that has ever grown, the thing whole civilizations built temples to face, is, from any real distance, completely average. That isn't a sad fact. It's the opposite. It means what happened here was not a freak accident. It means the ingredients are common. There are hundreds of billions of stars in this galaxy alone, and an enormous number of them are very much like ours. So when we ask how big the universe is, and we'll keep asking that all night, the sun gives us our first real answer in a new unit. 93 million miles is now simply 8 minutes and 20 seconds of light. 99.8% of everything nearby gathered into a single ordinary star. And that one unit, our brand new ruler, the distance that took us 400 steps past the moon to reach, we're about to need 30 of them just to get to the last planet, and 100,000 of them to reach the actual edge of the sun's territory. Let's start walking outward. Let that settle softly. Let your shoulders drop again, slowly. Somewhere out there light is still climbing gently out of a star, and none of it is in any hurry at all. Our new ruler is 1 astronomical unit, the distance from here to the sun. Let's find out how many of them the solar system is willing to spend. Mercury sits at about 4/10 of a unit. Venus at 7/10. Earth at 1. Mars at about 1.5. Those 4 are close together, the inner rooms of the house. Light crosses from the sun out to Mars in about 12.5 minutes. Then comes a gap, a wide, patient, quiet one. Past Mars lies the asteroid belt, spread between roughly 2 and 3.5 units. And despite every film you have ever seen, it is not crowded. If you flew through it at random, you would almost certainly never see a single asteroid. The average distance between them is hundreds of thousands of miles, further apart than the Earth and the Moon. That's worth pausing on, because it's the mistake almost everyone carries. Even the crowded parts of space are mostly nothing. Jupiter is at about 5 units. 5 times further from the sun than we are. Jupiter is enormous, more than 11 Earths across, and more massive than every other planet combined, twice over. Sunlight takes about 43 minutes to reach it. By the time light arrives there, it's older than a lunch break. Saturn is at 9.5 units. Uranus at 19. And Neptune, the last of the true planets, at 30. 30 astronomical units. 30 times our own distance from the sun. Sunlight takes 4 hours and 10 minutes to cross it. Stand on Neptune, if you could stand at all, and the sun would not look like the sun. It would be a point. Brilliant, yes. Brighter than anything in our night sky. Bright enough to cast a shadow. But a point all the same. No disk. No warmth on your face. An extremely good star, and nothing more. That is what 30 units does to the thing that dominates absolutely everything. Here's a way to hold the whole shape of it. Let your shoulders drop softly. Nothing here is urgent. Think of the sun as a house, and the planets as the rooms and the garden. The inner four are the house itself, kitchen, hallway, the rooms you actually live in. Jupiter and Saturn are the garden. Uranus and Neptune are the far end of the garden, where the grass stops being mown and nobody goes in winter. If you'd like it in real distances you could walk, here's the version people build on a quiet road. Shrink the sun to the size of a grapefruit and set it on the ground. Earth becomes a grain of salt, about 15 paces away. Jupiter is a small pea, roughly 75 paces off. And Neptune, the last planet, the far end of the garden, is another grain of salt, nearly half a kilometer down the road. You'd lose sight of the grapefruit long before you reached it. That's the whole solar system, laid out along a 5-minute walk. And in all that distance, the total amount of stuff you'd pass would fit comfortably in one hand. Which is the honest shape of it? Not a crowded family of worlds. A grapefruit, a few grains, and half a kilometer of empty road. Rest here a moment. Let the worlds drift past, without following any of them. And on that same scale, grapefruit sun, half-kilometer solar system, the nearest star would be another grapefruit about 4,000 kilometers away. Roughly the distance from London to the far side of Iran. 2 pieces of fruit, a continent and a half apart, and a few grains of salt near each one. That is the emptiest thing I know how to describe, and it is also the actual arrangement of matter in this part of the universe. There's one more thing about the outer planets worth carrying with you, because it's the reason any of this is quiet enough to have a conversation in. Jupiter is enormous, and it sits where it does, and its gravity has spent 4.5 billion years deflecting things. Some of what would otherwise have come inward towards us gets flung out of the solar system entirely, or captured, or broken up. The picture is more complicated than the old line about Jupiter being our shield. It also sends some things our way, but the traffic pattern of the inner solar system is unquestionably shaped by that one planet sitting 5 units out. We're not living in a calm neighborhood by luck alone. We're living downstream of something very large that has been tidying up for a very long time. And past Neptune, the solar system doesn't end. It simply stops being tidy. There's a wide belt of icy bodies out there, called the Kuiper Belt, spreading from about 30 units to around 50. Pluto lives there, along with millions of frozen fragments left over from the beginning, material that never quite got gathered up into anything at all. 2 of those outer worlds are worth a moment on their own, because they change what the word planet is doing. Uranus is tipped over. Not tilted the way Earth is, by a modest 23 degrees, but lying almost completely on its side, rolling around its orbit rather than spinning upright. Which means its poles take turns facing the sun directly, and a single season there lasts about 21 years. 42 years of continuous daylight at one pole, then 42 years of continuous night. Something hit it, most likely. Early on, hard enough to knock a world 4 times the width of Earth onto its side, and it has been rolling ever since. Let your breathing get slower and softer as we go further out. Neptune is the one that gets me, though. It was found in a way nothing else in the sky has been found. By the 1840s, astronomers had noticed Uranus wasn't keeping to its predicted path. It kept drifting slightly off, as though something were tugging at it. 2 mathematicians, working independently in France and England, took that tiny discrepancy and calculated where an unseen 8th planet would have to be to cause it. An astronomer in Berlin pointed a telescope at the predicted spot on a September night in 1846 and found Neptune within an hour, less than a degree from where the arithmetic said it would be. A planet found on paper first. Discovered by the mathematics of a wobble, then confirmed by looking. That is the same method, in miniature, that will later be used to weigh galaxies and find dark matter. Notice something not moving as it should, and deduce the presence of what you cannot see. I like that region more than I expected to. It's the part of the story where the building work simply stopped, where there was enough material to make another world, and not quite enough time, or not quite enough gravity, and so it stayed as pieces. 4.5 billion years later, it's still out there, unfinished, drifting in the cold, entirely at peace about it. So when we ask how far the solar system reaches, here's where we are. 30 units to Neptune, 4 light hours. 50 units to the far side of the Kuiper Belt. From the Sun to the last proper planet, light spends longer than most people spend asleep. And every one of those units is that 93 million mile ruler we picked up in the last chapter. Now, there is something of ours out there, past all of it, still moving. It left before most people listening tonight were born. It has been flying without a pause ever since, and it carries a recording of rain falling on a shore. It has not left the solar system. It isn't close. Breathe out, slowly and softly. Let the quiet planets drift past without following them. There is nothing to keep track of, and nothing here that needs you awake. There is one object out past the Kuiper Belt that we made ourselves, and its story tells you more about the size of things than any number I could give you. Voyager 1 left Earth in 1977. It has been flying outward without a single pause for nearly 50 years. It is now more than 160 astronomical units from the Sun, the most distant human-made object there has ever been, and almost certainly the most distant one there will be for a very long time. A radio signal from Voyager takes more than 22 hours to reach us. You could send it a message tonight before you sleep, and the reply would arrive the day after tomorrow. It's traveling at about 38,000 miles an hour. That's fast enough to cross the United States in about 4.5 minutes. Fast enough to go right the way around the Earth in under 40. Hold that speed in mind, because we're going to use it as a measuring stick in a moment, and it will not help nearly as much as you'd expect. It carries a golden record sounds, and images of Earth, sealed against the vacuum for whoever might one day find it. Greetings in 55 languages. A baby crying. Footsteps. Thunder. Waves on a shore. Rain. There's a moment in its story I think about often, and it happened on Valentine's Day, 1990. Voyager had finished its work at the planets and was heading out. An astronomer named Carl Sagan had spent years asking NASA to do something that had no scientific value whatsoever: turn the camera around and photograph the Earth on the way out. There were sensible objections. Pointing the camera back meant pointing it near the sun, which risked damaging it. And the picture would show nothing. Earth would be far too small to resolve. They did it anyway. The photograph came back with the Earth occupying less than a single pixel. A pale dot sitting by chance inside a band of scattered sunlight, looking like a speck of dust caught in a sunbeam. That's what our entire world looks like from 4 billion miles away, which, by tonight's standards, is barely out the front door. We haven't even reached the end of the garden yet, and home has already stopped being visible. Take another gentle breath. Let the distance stay comfortable rather than heavy. It is running out of power slowly. The instruments are being switched off one by one to keep the rest alive a little longer, and one day soon, within a few years now, the last of them will go quiet, and we will stop hearing from it. The people who fly it still work in shifts. Its onboard memory is measured in kilobytes, less than a single photograph from the phone beside your bed, by a factor of thousands. The commands go out in a programming language almost nobody alive still writes, from a team who have kept a 50-year-old machine talking across 16 billion miles of nothing. But it won't stop. That's the part people miss. It will keep going, silently, for millions of years, carrying the sound of rain across an ocean that has no other side and no far shore to reach. There's no wind out there to slow it. Nothing to run into. Nothing to bring it home. It is a boat that left the harbor and simply kept going, and the harbor is us. And here is the thing that puts our entire climb so far into its proper place. Let your body sink a little deeper into the bed. There is nothing to reach for. For all of that, 50 years of unbroken flight, 160 units, 4 minutes across America, a golden record, and a dying power supply, Voyager has not left the sun's territory. Not nearly. Not remotely. Because there is one more region beyond it, and it is far, far larger than everything we have crossed tonight put together. So when we ask what the far reaches of the solar system look like, Voyager gives us the honest answer, and it isn't a number, it's a proportion. 50 years of the fastest sustained travel our species has ever managed. 160 times the distance from here to the sun. 22 hours for its voice to reach us. And it is still, by any reasonable measure, in the sun's back garden. How much garden is left? Voyager will need about 300 more years just to reach the inner edge of it, and something like 30,000 years to come out the other side. Rest gently a moment. Let the quiet of that place stay quiet. Nothing out there needs watching tonight, and nothing out there is in a hurry. Far out past everything we've crossed, past Neptune, past the Kuiper Belt, past Voyager and its dying batteries, there is thought to be one more thing wrapped around all of it. I want to be careful with the words there. Thought to be, because this is the first stop on tonight's climb that nobody has ever seen. It's called the Oort Cloud, and it is an enormous shell of icy bodies surrounding the sun on every side. We have never observed it directly. It is too faint, too cold, too scattered, and too far. What we have are the comets, the long period ones that occasionally fall inward and swing past us on paths that take thousands of years. They arrive from every direction at once, evenly, from all over the sky. And that single observation tells us something remarkable. Whatever they're falling from isn't a disk. It's a sphere. A vast, thin, spherical shell, entirely surrounding us. The inner edge may begin around 2,000 astronomical units. The outer edge may reach something like 100,000. 100,000. Remember where we've been. Neptune is at 30. Voyager, after half a century of the fastest flight we've ever managed, is at 160. So if the Oort Cloud is real, and almost everyone who studies this believes it is, then Voyager is not 1% of the way to the far edge of our own solar system. It is not 1/10 of 1%. It will take another 300 years or so just to reach the inner boundary, and something like 30,000 years to pass out through the far side. 30,000 years. Longer than agriculture. Longer than writing. Longer than any city that has ever stood, by a factor of 10. Just to leave the sun's own back garden. Here's the shape of it, if it helps. We said the solar system was a house with a garden. The Oort Cloud is what you find when you walk to the end of the garden looking for the fence and discover there isn't one. The lawn just gets longer and thinner and darker and keeps going, and eventually, you're not sure whether you're still in the garden or somewhere else entirely, and there is no gate to tell you. The sun's territory doesn't end. It fades. And here's what makes that genuinely strange, rather than merely large. Breathe softly. Let the darkness out there stay peaceful, not empty. If the Oort Cloud really does extend a light year and a half in every direction, and the nearest star is 4.2 light years away, then that star has its own cloud, extending its own light and a half outward, reaching towards us. Which means the two clouds may very nearly touch. There may be no true gap at all between our solar system and the next one. Just a thinning and a mingling, and somewhere in the middle, a region where an icy body a mile across drifts in the dark, faintly pulled by two different suns, belonging to neither. Nobody has ever seen that place. Nobody ever will. But if the models are right, it is out there, and it is where our address quietly stops being ours. We've also had a visitor from beyond it. In 2017, a small object swept through the inner solar system on a path that could not possibly have been a closed orbit. It came from outside, passed the sun once, and left forever. It was the first confirmed interstellar object anyone had ever seen, and it was here for a matter of weeks before it was gone. Which tells you something quietly reassuring. The doors between these systems are not locked. Things do cross. They just take an extremely long time about it. I want to be careful here, because this is the point in the climb where it would be very easy to make you feel small in an unpleasant way. That is not what's happening. Here's what's actually happening. We have spent an hour walking steadily outward, and we have not yet finished with a single star. Not one. And the reason isn't that we're insignificant. It's that emptiness is the ordinary condition of things, and we happen to live in one of the extremely rare places where it isn't empty. Rarity is not smallness. A warm room on a cold night isn't made any smaller by the size of the night around it. Let that quiet settle over you. Rarity is not smallness, and neither is stillness. So when we ask where the sun's reach ends, the honest answer has three parts. It ends somewhere around 100,000 astronomical units out, in a shell we have never seen and know only from the paths of falling comets. It would take our fastest object 30,000 years to cross. And measured in light, our ruler for the rest of the night, the outer Oort Cloud sits about 1.5 light years from the sun in every direction. Light years. We've finally arrived at that word. And we've arrived at it for a reason. From here, astronomical units become useless. Writing distances in units of 93 million miles is about to become as clumsy as measuring the gap between cities in shoe lengths. So we change rulers one last time. And this time, we won't change again for the rest of the night. Let your breathing slow, softly. Feel how gently the bed holds you. All that quiet cold out there only makes this small warm place warmer. A light year is the distance light travels in 1 year. That's the whole definition. But definitions are cheap, so let me build it for you instead. Light goes around the Earth 7.5 times every second. We established that back at the very first step, when the world was still the biggest thing we had. Now let it run for a full year without stopping. No slowing. No resting. 365 days at 186,000 miles per second. That distance is about 6 trillion miles. 6 trillion. 6 million million. It is not a number to picture. It's a number to hand over to the word light year and then never think about again, which is precisely why the word exists. And here's tonight's fifth question. Asked again, now that we finally have the right ruler in our hands, how big is the universe, really? We're going to spend the rest of the night answering that in light years. So let's find out what one of them buys us. The nearest star to our Sun is called Proxima Centauri. It's small and cool and red, much smaller than our Sun, and so faint that you cannot see it with your eyes alone, despite it being our closest neighbor in the entire universe. It sits 4.2 light years away. 4.2. After everything we have climbed through tonight, the very next star along is a distance we can write with 2 digits and a decimal point. That feels almost friendly. It isn't. Let me put it in the only terms we've earned. Voyager 1, our furthest traveler, 4 minutes across America, 50 years of unbroken flight, would need roughly 73,000 years to cover 4.2 light years. 73,000 years. And that is to the closest star there is. The one next door. Here's the picture I'd like you to fall asleep holding. Shrink the entire solar system, the Sun, all 8 planets, everything out to Neptune's orbit, down to the size of a dinner plate sitting on the table in front of you. At that scale, Proxima Centauri would be another dinner plate, sitting about a mile away. 2 plates, a mile of empty air between them, and essentially nothing at all in that mile. Let your body rest softly. The distances are quiet ones. That is the actual texture of the galaxy. Not a crowded sky full of stars nearly touching. Islands of light, separated by distances so large that nothing we build will ever cross them quickly. And Proxima isn't alone out there. It belongs to a system of 3 stars, 2 sun-like stars orbiting each other closely, and Proxima itself circling the pair at an enormous distance, taking hundreds of thousands of years to complete a single lap. Around Proxima, we found planets. At least 2. One of them sits in what's called the habitable zone, the band of distance, where liquid water could exist on a surface. I want to be careful with that phrase, because it promises more than it delivers. Habitable zone means the temperature might allow water. It doesn't mean anything lives there. Proxima is a red dwarf that throws violent flares, and any planet close enough to stay warm is close enough to be scoured by them. But the fact remains, and it's worth saying plainly on a night about scale, the very first star along, the closest one there is, has worlds going around it. We did not have to search far to find that. We looked next door, and next door had planets. Let your breathing slow again here. The distances can wait. If planets were rare, the nearest star would almost certainly have none. It has at least 2. There's a thought experiment I like about that distance, and it costs nothing to run. Suppose you decided, tonight, to send a message to Proxima. Not a spacecraft, just a radio signal, traveling at the speed of light, the fastest anything can go. It would arrive 4 years and 2 months from now. If anything were there to hear it and answer immediately, the reply would reach you 8 years and 4 months after you sent it. 8 years for one exchange. With the closest star there is. Now, hold that against the rest of tonight. Andromeda is 2.5 million light-years away. A single question and answer would take 5 million years, longer than our species has existed, twice over. Which means something worth being clear about, because it's the honest emotional shape of these distances. Conversation at cosmic scale is essentially impossible. Not difficult, structurally impossible for anything with a lifespan. We have sent a few deliberate signals outward over the years, aimed at various places. They're still traveling. The nearest of them has covered a few dozen light years, a step across the room, on the scale of the galaxy. And I don't find that lonely, particularly, though I understand why people do. Here's why. The same speed limit that stops us talking to anyone also means the sky is full of arrivals. Everything you look at up there is something reaching you. Light that left Proxima before your last birthday. Light that left Betelgeuse before Shakespeare. Light that left Andromeda before there were people. We can't hold a conversation with any of it. But we are, constantly and without effort, being spoken to. Every clear night, the entire history of the universe is queued up above your roof, arriving in order, oldest at the back. And now that we have light years, the time delay arrives in full. Proxima's light is 4 years and 2 months old when it reaches us. When you look in its direction, you're seeing something that happened before whatever you were worrying about last spring. Rest gently a moment. You do not have to cross anything tonight. The bright stars you know by name are older still. Betelgeuse, the red shoulder of Orion, is somewhere around 600 light years away. Its light left before Shakespeare was born. Deneb, high in the Summer Triangle, may be over 2,000 light years distant, which means the light landing on your eye tonight set out while the Roman Empire was still deciding what it wanted to be. The night sky is not a photograph of now. It's a room full of clocks, every one of them showing a different time, and not a single one of them showing this one. So when we ask what a light year buys us, 6 trillion miles, 4 and a bit of them, to the nearest star, 73,000 years of Voyager to get there. 2 dinner plates, 1 mile apart, with nothing in between. Let's take stock, because we're a third of the way up the staircase, and the view has changed completely. The Earth, a little under a 20th of a light second across. The Moon, 1 1/3 light seconds away. The Sun, 8 light minutes. Neptune, 4 light hours. The edge of the Oort Cloud, a 1.5 years of light. The nearest star, 4.2 years. Every step has swallowed the one before it whole. And we are still, at this hour, entirely inside one small neighborhood of one galaxy. Before we leave that neighborhood, I want to do something small and rather grounding. I want to count what you can actually see with your own eyes. The number is smaller than you'd think. Much smaller. Take another slow, soft breath. Let the distances rest where they are, quietly. You do not have to cross any of them tonight. We've just measured the gap to the nearest star. Now let's do the opposite. Let's stop measuring outward for 10 minutes and count what's actually visible from where you are. On a genuinely dark night, no streetlights, no moon, no haze, a person with good eyesight can see somewhere around 2,500 stars at any one moment. Across the whole sky, over a whole year, from both hemispheres, the total comes to around 9,000. 9,000 stars. And it's worth knowing that somebody actually counted them, long before anyone could photograph the sky. In the 2nd century BC, a Greek astronomer named Hipparchus catalogued around 850 stars by eye, position, and brightness, one at a time. He invented a scale for the brightness, calling the brightest ones first magnitude, and the faintest he could see 6th magnitude. That scale is still in use. Every time an astronomer today says a star is magnitude 4, they are using a system built by a man with no lens, no clock as we'd recognize it, and no way to write down a decimal. He also did something else, and it is one of the great acts of patience in the history of the species. By comparing his own measurements against records from 150 years earlier, he noticed that the whole sky had shifted very slightly against the seasons, and from that, he discovered the slow wobble of the Earth's axis, a cycle that takes 26,000 years to complete. He detected a 26,000-year motion using a century and a half of notes. That is the entire visible universe, as far as every single human being who lived before about the year 1600 was concerned. Every myth, every constellation, every navigation chart that ever crossed an ocean, every story anyone ever told a child about the sky, all of it built from 9,000 points of light. From a city, of course, it's far fewer. From the middle of a large town, you might see 50. Some people have never seen more than a dozen stars in their lives, and have never once seen the band of the galaxy overhead, which we'll come to shortly, and which is directly above your roof right now, whether you can see it or not. Take a slow, calm breath. Let the sky above the roof be enough. That last part isn't a figure of speech. Roughly a third of everyone alive cannot see the Milky Way from where they live. In some countries, it's closer to 2/3. It hasn't gone anywhere. We've simply put enough light between ourselves and it that the sky above most cities now stops at about 50 stars. There's a story from Los Angeles that gets told about this, and whether or not every detail survives retelling, the shape of it is true. In the early hours of a January morning in 1994, An earthquake knocked out power across the city. People went outside in the dark, frightened, looking up, and a number of them reportedly called emergency services and observatories to ask about a strange silver cloud stretching across the sky. It was the Milky Way. Many of them had simply never seen it before. I find that neither funny nor sad, particularly. It's just a very clear measurement of something. Not of the sky, of us. The galaxy has been directly overhead every single night of every human life that has ever been lived, and within about 3 generations, we managed to hide it from most of ourselves with streetlights. Now here's the part that puts the whole evening into place. Almost every star you can see with your unaided eyes lies within about 1,000 light years of us. A few of the brightest are further. Deneb may be 2,500 or more, but the great majority are close neighbors by galactic standards. So the sky you know, the one in the poems and the paintings, is a bubble, roughly a couple of thousand light years across. Our galaxy is 100,000 light years across, which means everything anyone has ever seen by eye alone sits inside a bubble about 2% the width of our own galaxy. And in volume, because volume grows as the cube of the width, it's a fantastically small fraction of 1%. 2,500 stars out of a few 100 billion. Roughly 1 star in every 80 million. Picture a vast hall in the dark, a cathedral, or a great warehouse, with the far walls too distant to make out. Let your thoughts drift wherever they like. Nothing needs following. Somebody lights a single candle in the middle of it. You can see the flame and the few feet of floor around it, and the faces of anyone standing close. Everything else is there: the pillars, the walls, the roof beams, the whole enormous structure, but it is simply beyond the reach of that one small light. That candle is your eye. The hall is the galaxy. And working from inside that little pool of candlelight, using nothing but patience and geometry, people still worked out that the Earth moves, that the stars are other suns, and that the faint band of light overhead is a galaxy seen edge-on from within. That is the thing I find genuinely moving about all of this. Not the size of the universe. The size of what got figured out from a very small, very badly lit sample. So when we ask how much of the universe you can actually see, about 2,500 stars at a time. 9,000 across a lifetime and a whole planet. Almost all of them within 1,000 light years. 1 star in every 80 million our galaxy holds. The sky you know is not the universe. It's a candle. And there's one more thing about that visible sky I should tell you before we widen out, a gentle correction to something we all grew up believing. The patterns up there. The hunter, the bear, the plow, the twins. None of them are real. Let your eyes stay softly closed. Let the quiet sky above the roof do what it has always done, gently, without needing you awake for it. I should be precise about what I mean by that, because it sounds more dismissive than it is. The constellations aren't real in one specific sense. The stars in them have nothing whatsoever to do with each other. They aren't neighbors. They aren't groups. They don't orbit anything together, and most of them have never been anywhere near one another in the whole history of the universe. They only look arranged because we are seeing them flattened onto the inside of an imaginary dome, as though someone had painted them all on the same ceiling. Take Orion, the easiest shape in the winter sky, and the one nearly everyone can find. The 3 stars of his belt look evenly spaced, evenly bright, laid out as if by hand. In reality, those 3 stars sit at wildly different distances. Alnitak is around 1,300 light-years away. Alnilam is nearly 2,000. Mintaka is somewhere near 1,200. They are hundreds of light-years apart from each other, in a straight line only from here and only from now. Move a few hundred light-years in any direction, and Orion doesn't rearrange itself into a different shape. It dissolves. The belt scatters. The shoulders drift apart. The hunter simply stops existing, because the hunter was never anything more than an alignment. Every constellation you know is a temporary accident of one particular viewpoint, from one small planet, over a few thousand years, which is a long time to us and no time at all to the sky. And they're not even stable from here. The stars are all moving, individually, in different directions and at different speeds. We don't notice, because the distances are so large that the motion takes millennia to show. Take the plow, the Big Dipper, if that's the name you grew up with. 7 stars, one of the most recognizable shapes in the northern sky. 5 of the 7 are actually related. They were born together and travel together. The 2 on the ends are not. They're passing through from other directions entirely. Breathe out slowly. Let the shapes come apart gently, the way they always were. So the shape is slowly coming apart. 100,000 years ago, the handle bent the other way. 100,000 years from now, the pan will have lost its shape completely, and the handle will have folded. Nobody will be able to see a plow in it, and whoever is looking up will find something else in those stars and name it and be just as certain. It's also worth saying that the shapes were never universal. Different cultures looked at the same lights and drew completely different things. The same stars that formed a hunter for one people formed a canoe for another, a caribou for another, and for another, the outline of a bird carrying a river. None of them were wrong, because there was never anything up there to be right about. You've seen this effect yourself, if you've ever come into land at night. Look down at a city from a plane, and the lights make shapes. A curve here, a bright line there, a cluster that looks like something. Move a few miles along, and the shapes are gone. The lights haven't moved. Nothing has changed on the ground. Your angle changed, and that was enough to dissolve every pattern you'd found. The constellations are that. run over hundreds of light years instead of a few miles. I find that oddly comforting rather than disappointing, and I'd like to explain why before we move on. It means the patterns up there were never discoveries. Nobody found the hunter. Nobody uncovered the bear. Those shapes are not out there waiting to be noticed by a sufficiently clever species. They were company. People looked up at a scattering of completely unrelated lights thousands of years ago and drew hunters and bears and plows and sisters and gave them names and stories and quarrels and passed them down through 50 generations and used them to cross oceans and plant crops and find their way home in the dark. The universe supplied the dots. We supplied absolutely everything else. So when we ask what the constellations actually are, not groups, not neighbors, not structures, chance alignments of unrelated stars at wildly different distances, viewed from one particular seat in one particular century. Orion's belt is spread across 800 light-years of depth and looks like a straight line only from here. Rest quietly here. There was never anything up there you had to hold on to. And when you go outside tonight, or tomorrow, or next week, and look up, you'll be doing exactly what everyone before you did. Seeing a tiny, close, unrepresentative handful of stars, arranged in shapes that aren't there, and feeling something anyway. That is not a failure of perception. That's simply what it is to be inside a very large thing, looking out with the eyes you happen to have been given. Now let's step back far enough to see the structure those 9,000 stars actually belong to. It's been above your roof the entire time we've been talking. You've probably seen it and mistaken it for cloud. Breathe slowly and gently here. Let the shapes drift softly apart. There was never anything up there you had to hold, and nothing to solve. All those stars, the 9,000 you can see, the 30 within 12 light years, the hundreds of thousands within 500, they belong to something. They aren't scattered at random through empty space. And that something is so large that we have been standing inside it all night without once mentioning it. Our galaxy is about 100,000 light years across. Take that in slowly, using everything we've built tonight. Light takes 4.2 years to reach the nearest star. To cross our galaxy from one side to the other, light needs 100,000 years. If a beam of light had set out across our galaxy at the moment the first recognizably modern humans appeared in Africa, before language as we'd know it, before any tool more complicated than a shaped stone, before fire was reliably kept, that beam would be arriving at the far side just about now. That is one galaxy. One. Inside it, there are somewhere between 1 and 400 billion stars. The number is uncertain, and the uncertainty itself tells you something. We can't count them, so we weigh the galaxy and estimate. When your margin of error is 200 billion stars, you are dealing with something outside ordinary bookkeeping. Our Sun is one of them. It sits about 26,000 light-years from the center, roughly 2/3 of the way out, in a quiet stretch between two of the major spiral arms. Not the center, not the edge, a calm suburb, and it's moving. The entire solar system, Sun, planets, Voyager, the Oort Cloud, all of it, is orbiting the galactic center at around 500,000 miles an hour, carrying us along with it. One complete lap takes about 230 million years, which means the last time the Sun was in this exact spot in its orbit, the first dinosaurs were just appearing. Our star has been around the track perhaps 20 times since it formed. 20 laps. That's the entire age of the Sun, measured in galactic years, a number small enough to hold in one hand. At the center of all that turning, there is a black hole about 4 million times the mass of the Sun. It sits there quietly, mostly not eating anything at all, marking the still point at the center of the wheel. Let your breathing stay slow. The quiet turning carries on gently. We photographed it a few years ago, not the hole itself, which cannot be photographed, but the ring of glowing matter around it, using telescopes spread across the entire Earth, working together as a single instrument. I mention it partly because it's remarkable, and partly for the scale lesson hidden inside it. That black hole, 4 million suns of mass, is a small feature of the galaxy. Important, but small. The galaxy does not orbit it the way planets orbit our Sun. Even the monsters are minor at this altitude. There's also more of the galaxy than the part that shines, and it's the majority of it. The stars and gas we can see sit inside a much larger, roughly spherical cloud of something invisible, a halo that extends far beyond the visible disk, possibly out to 250,000 light-years or more. We cannot see it. We know it's there because of how the outer parts of the galaxy rotate. They move too fast for the visible mass to hold them, and yet they stay. So the thing you see as a milky band is not the galaxy. It's the lit part of the galaxy, sitting inside something much larger and entirely dark. Let your breathing settle. The wheel has been turning a long time without needing you awake. And the galaxy has been eating. Around us, right now, there are streams of stars strung out in long arcs across the sky, the stretched out remains of smaller galaxies that came too close and were pulled apart over billions of years. We can trace them. They're still moving in formation, faintly, like the wake behind a boat that passed long ago. We are, in other words, standing inside something that has been steadily assembling itself out of its neighbors for most of the age of the universe, and has not finished. There's one more feature of our galaxy I'd like to give you, because it's the one that connects the whole structure back to your body. Our galaxy is not just a collection of stars. It's a factory, and it has been running for 13 billion years. The first stars were made almost entirely of hydrogen and helium, because that is nearly all the early universe had. Everything heavier, carbon, oxygen, nitrogen, iron, calcium, had to be built inside stars, fused together under pressures nothing else in the universe can produce, and then released when those stars died. Some of them released it gently, blowing off their outer layers over thousands of years. Some released it in the enormous explosions that briefly outshine an entire galaxy. Either way, the material spreads out, mixes with the gas already there, and eventually collapses again into a new generation of stars, each one slightly richer in heavy elements than the last. Our Sun is a late-generation star. It formed from a cloud that had already been enriched by countless earlier ones, which is why there were enough heavy elements lying around to make rocky planets at all, and why there was iron available to end up in your blood. The galaxy is not the setting of the story. It's the machinery that made the ingredients. Every atom heavier than helium in your body was manufactured somewhere in this 100,000 light-year wheel by a star that had to die to release it, long before the Earth existed. Not one of those stars had any idea what it was making. Here's why it looks the way it does, and it's the simplest explanation in astronomy. Take a soft breath. Let the slow turning carry you rather than the other way round. Stand in the middle of a forest and look straight up. You see sky, a few branches, gaps. Now look sideways, along the ground. The trees pile up behind one another until they become a solid wall of trunks, and you can't see through at all. You're in a disk of stars. Look up out of the disk, and you see a few. Look sideways along it, and they pile up into a band. That's it. That faint milky stripe arching over your roof on a clear night, the one you might mistake for cloud, is the galaxy seen edge on from the inside. Which means you have already seen this structure. With your own eyes, without any instrument, probably as a child. 100,000 light-years of stars, and it looks like a smudge you'd miss if nobody told you to look. So when we ask how big our galaxy is, 100,000 light-years across, somewhere between 1 and 400 billion stars. Our Sun, sitting 2/3 of the way out in a quiet suburb, 20 laps into its life, being carried at 500,000 miles an hour, without any of us feeling a thing. And we have never seen it from outside. We never will. Every picture you've ever seen of the Milky Way from above is a reconstruction, built entirely from measurements taken from a single fixed seat in the 11th row. And still we mapped it. Before we leave our galaxy for good, I want to stop the outward climb for 10 minutes and try something completely different. Not distance this time. Quantity. There's an old comparison about sand that almost everyone has heard, almost nobody has checked, and it turns out to be far stranger than the version people tell. Rest quietly now for a moment. Let the great slow wheel turn gently without you. It has been turning calmly for 13 billion years and will manage tonight. The comparison goes like this. There are more stars in the universe than there are grains of sand on Earth. You've heard it. It's been repeated so often the words have gone smooth, like a coin in a pocket. Let's take it out and actually look at it, because when you do the arithmetic honestly, it doesn't come out the way the saying suggests. So let's count the sand. People have genuinely tried. You take an estimate of the world's beaches and deserts, an estimate of the depth of sand in them, and a count of grains per handful, and you multiply very carefully and admit a large margin of error. The figure that keeps coming out is somewhere around 7.5 quintillion grains. 7.5, followed by 18 zeros. Every beach, every dune, every stretch of shoreline on every island in every ocean. All of it, 1 grain at a time. Now the stars. Our galaxy holds a few 100 billion, but ours is one of the large ones, and most galaxies out there are far smaller, some holding only a few million. So nobody multiplies 2 big numbers together and calls it an answer. Instead, you survey a patch of sky, work out the mix of galaxy sizes in it, and scale carefully upward. When astronomers do that, the estimates for the total number of stars in the observable universe commonly land somewhere around 10 sextillion, a 1 with 22 zeros after it. I want to be honest about those 2 numbers. Both are estimates, not measurements. Nobody counted. The margin on the star figure could be a whole factor of 10 either way. But even allowing for that, the comparison isn't close. 7.5 quintillion grains of sand, 10 sextillion stars. The stars win by a factor of something like 1,000. So the old saying isn't just true. It badly undersells it. For every single grain of sand on every beach on this entire planet, there are roughly 1,000 stars. Here's the version to fall asleep on. Imagine crouching at the water's edge on a beach at night and picking up 1 handful of wet sand. Maybe 10,000 grains, easily held in 1 palm, cold and heavy and gritty against the skin. That handful stands for 10 million stars. Let your hand relax, the way it would if the sand were really pouring out of it. Now open your fingers and let it pour back onto the beach. In those few seconds, you've released more suns than the human eye has ever counted, several thousand times over. And the beach goes on in both directions in the dark. There's a second comparison hiding inside that handful, and it runs the opposite way. Pick out 1 single grain. Just 1, sitting on your fingertip, barely visible, the sort of thing you'd brush off without noticing. That 1 grain contains somewhere in the region of 50 quintillion atoms. Which is more atoms in that single grain than there are grains of sand on every beach on Earth? By a factor of several. So the comparison folds back on itself. The sand is to the stars as the atoms are to the sand, and you're holding both ends of it at once, in one hand, on a beach at night. That's the thing about scale that took me longest to accept. It doesn't only run outward. It runs down as well, just as far, just as absurdly. We happen to sit somewhere near the middle of the range, which is probably why neither direction feels natural to us. You are, very roughly, about as many times larger than an atom as a star is larger than you. We are the midpoint. Not the center of anything, not the purpose of anything, but the place where the two staircases meet, and the only place either of them gets noticed. And there is a second half to this comparison that almost nobody mentions. Every one of those stars is a sun. Not a point of light, a sun. A furnace turning millions of tons of matter into light every second, exactly the way ours does, in a system very likely to have planets of its own. We've now confirmed several thousand planets around other stars, and the pattern from that sample suggests planets are not rare at all. They may simply be the ordinary outcome of making a star, the way a wake is the ordinary outcome of a boat. So the number isn't 10 sextillion lights. It's 10 sextillion suns, with, quite plausibly, more worlds than suns. Breathe slowly. Let the numbers pour away too. They were only ever pointing at something. I'm not going to draw any conclusion from that tonight. It isn't that kind of journey, and speculation isn't restful. I'll only say that whatever else is true, we are not looking at a sparse universe. We are looking at an extraordinarily generous one that appears to make stars and worlds the way a shoreline makes sand, in quantities nobody asked for and nobody can count. So when we ask how much is out there, rather than how far, 7.5 quintillion grains of sand on Earth, 10 sextillion stars, give or take a factor of 10. 1,000 suns for every grain. 1 handful equals 10 million. Let that settle, and then let it go. There is nothing you need to do with a number like 10 sextillion. It doesn't ask anything of you. It's simply the size of the container we happen to be in, measured, checked, and quietly enormous. Now let's start climbing again. And the next step is the largest single jump of the entire night, because we're about to leave our galaxy altogether, and the very next thing out there is 2.5 million light years away. You can see it with your naked eye. Let your hands rest softly. Let the numbers drift quietly away. They were only ever a slow way of pointing at something, and the pointing is gently finished. Our galaxy has neighbors. The nearest large one is called Andromeda, and it sits about 2.5 million light-years away. 2.5 million. We've jumped from 100,000 to 2.5 million, and the jump was a single step. 25 times in one move. Andromeda is bigger than us. Perhaps twice as wide, holding something like 1 trillion stars. And here's the part people rarely believe the first time they hear it. You can see it. On a very dark, clear night, in the right season, with your own eyes and nothing else. A faint oval smudge, dimmer than anything you'd normally notice, easy to look straight past. That smudge is the most distant object visible to the human eye without any instrument at all. Its light is 2.5 million years old. It left before our ancestors were recognizably human. It has been traveling that entire time, through all of it, the whole history of our species happening somewhere off to one side while it crossed, and it ends its journey inside your eye, on a cold night, while you stand in a field wondering whether you're actually seeing anything at all. You are? That's the light. It got here. Astronomers in the 1920s used to call galaxies island universes, and the phrase stuck because it's exactly right. Think of standing on the shore of an island at night and seeing, far across the water, the lights of another island. You can't get there. You have no boat, and there will never be one. But you can see it clearly enough to know there are hills over there, and that the lights are arranged in a pattern, and that it is quite a lot larger than the island you're standing on. That's the whole relationship. 2 islands. A very great deal of dark water. We have company too, and ours is visible, though only from half the world. If you live in the southern hemisphere, or have ever traveled far enough south, you may have seen 2 faint smudges of light in the night sky, well away from the band of the Milky Way. They look like detached pieces of it, as though someone had torn off 2 small fragments and set them adrift. They're called the Magellanic Clouds, and they are galaxies. Small ones, the larger holds a few billion stars, the smaller, rather fewer, but genuine galaxies, orbiting ours, about 160,000 light-years away. Let your body settle. That light drifts gently towards us. Sailors used them for navigation long before anyone knew what they were. They were named in European charts after a voyage in the 1500s, though people living under those skies had known them and named them for many thousands of years before that. And they are being taken apart. There is a vast stream of hydrogen gas trailing behind them, pulled out over the last billion years or so by our galaxy's gravity, arcing across a huge fraction of the southern sky in wavelengths our eyes cannot see. That gas will eventually fall inward and become new stars in the Milky Way. So the 2 brightest galaxies visible to the naked eye from the southern hemisphere are, slowly, becoming part of ours. I like that the sky has a north and south version of the same lesson. From the north, you see Andromeda, the galaxy that will one day merge with us as an equal. From the south, you see the clouds, the galaxies we are quietly absorbing. Same process, two directions, and both of them visible from the ground with nothing but your eyes and a dark night. Take a gentle breath here. That light has been traveling calmly for 2.5 million years. Andromeda has company of its own too. At least a dozen smaller galaxies orbit it, and 2 of them are bright enough to have been catalogued centuries ago as fuzzy patches near the main smudge, small, dense, elliptical things, each holding a few billion stars, circling the big spiral the way our own small companions circle us. And there's something odd at the middle of it that took decades to make sense of. When astronomers looked closely at Andromeda's core, they found what appeared to be 2 separate bright nuclei sitting side by side, rather than one. The favored explanation now is that it isn't 2 objects at all. It's a lopsided ring of old stars orbiting the central black hole on stretched, elongated paths, spending more time at the far end of the loop and therefore piling up there, the way traffic bunches on the slow side of a bend. So the brightest false impression in the nearest galaxy turns out to be a Q. I mention it because it's a good reminder of how this all works. Almost nothing out there arrives already understood. It arrives as a smudge, or a double dot, or an anomaly in a column of numbers, and then somebody spends 30 years working out what shape would produce that appearance from here. Every clean fact I've given you tonight was once an argument. Andromeda is also coming towards us. Most galaxies are receding. We'll come to why later tonight. But this one is falling our way at about 250,000 miles an hour. In roughly 4 billion years, the 2 galaxies will meet. It sounds violent. It won't be, in the way you're imagining. Remember the dinner plates a mile apart. Stars are so extraordinarily far from each other that when 2 galaxies collide, essentially no stars hit anything at all. The 2 structures will pass through one another, stretch into long, luminous streams under gravity, fall back, and eventually settle into a single larger galaxy. The sky would change. Slowly, over hundreds of millions of years, and nobody standing underneath it on any given night would be alarmed. It would simply be the way the sky was, for whoever was there to see it. Let your body get heavier. 4 billion years is a long way off, and none of it is tonight. If you want the picture, over a few 100 million years, that faint oval would grow. First to the size the moon appears, then larger. Eventually, it would fill a quarter of the night sky, a great silent wheel of light hanging over every landscape on Earth, brighter than anything except the moon itself. Then the 2 would pass through each other. new stars would form in enormous numbers where the gas clouds collided, the whole sky lighting up with star formation over tens of millions of years, which sounds violent and would look, from the ground, like an extremely slow and beautiful weather system. And then it would settle. The spiral arms of both galaxies would be gone, wound and stretched into something rounder and dimmer. The Milky Way, as a shape, would stop existing. Whatever is standing on whatever planet would look up at a sky with no band across it at all. The sun will very probably survive all of it, untouched, along with whatever is left of this solar system, just carried onto a different orbit inside a different galaxy. I find that a strangely comforting note to fall asleep on. The largest collision our galaxy will ever experience is scheduled, predictable, and would be survivable by anyone standing on this exact spot. The end of the Milky Way is not a catastrophe. It's a merger, and it takes longer than the entire history of animal life on Earth. So when we ask what's next door, Andromeda, 2.5 million light-years off, twice our width, 1 trillion stars, visible to your naked eye as a smudge, falling towards us at 250,000 miles an hour, arriving in 4 billion years. And when it arrives, essentially nothing will collide. But Andromeda isn't alone out there either, and neither are we. There's a structure above the galaxy, and another one above that, and another above that, and each one is roughly 100 times larger than the last. We're going to climb 3 of them in the next 10 minutes. Take a slow, soft breath. Let that quiet light finish its gentle journey. 4 billion years is a long way off, and none of it is tonight. Galaxies are not scattered evenly through space. They gather. And the gatherings gather. So let me give you the address, working outward, one line at a time. Think of it exactly the way a postal address works. House, street, town, county, country, continent. Each line contains the one above it and means nothing without the ones below. The house is the solar system. 93 million miles to the sun, a light year and a half to the far edge of the Oort Cloud. The street is our stellar neighborhood, the 30 stars within 12 light years, the 2,000 within 50. The town is the Milky Way. 100,000 light years across, a few 100 billion stars, our sun 2/3 of the way out. The county is the local group. Our galaxy, Andromeda, and about 80 smaller galaxies spread across roughly 10 million light years and held loosely together by gravity. Most of the members are small, dim, ragged little galaxies orbiting the 2 big ones like moths around 2 lamps. Some contain only a few million stars, which by galactic standards is barely a village. The country is harder to name than the others, and I want to be careful here, because this is the line where the postal address stops being a tidy set of boxes. 54 million light-years away lies the Virgo cluster, a dense crowd of more than 1,000 galaxies, all falling around a common center. It is the nearest great city in this part of the universe. We are not in it. We live quietly out past its edge, in the countryside, drifting slowly towards it. So the address stops nesting neatly at this level and becomes a quiet matter of which way things are slowly falling. That's worth knowing, because the next lineup was only worked out because somebody stopped asking where galaxies are and started asking where they are going. And the continent is Laniakea. In 2014, astronomers mapped the motions of thousands of galaxies, not their positions, their motions, and found that we belong to an enormous connected structure, a basin of attraction they named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is about 520 million light-years across and contains something like 100,000 galaxies, all drifting on the same slow current. Breathe softly. Let the current carry you along with everything else. That's the word I want you to hold, current. This isn't a static filing system. Everything in that 500 million light-year structure is flowing, slowly, in the same direction, including you and your bed and the room you're in, right now, tonight. We are not just in a galaxy. We are in a galaxy, in a group, in a cluster, in a supercluster, and every one of those levels was discovered in the last 100 years or so. And there's a destination on that current, which is the part I find hardest to put down. Our whole local group is falling. Not drifting, falling, towards something. We're moving at about 1.33 million miles an hour relative to the background of the universe itself, and everything nearby is going the same way. For decades, nobody could see what we were falling towards, because it sits behind the plane of our own galaxy, hidden by the dust and stars of the Milky Way, in a region astronomers simply call the zone of avoidance, because you cannot look through it. They named the thing we're falling towards the Great Attractor, which is an unusually honest name. It means the large thing pulling us, whatever it is. We now think it's a colossal concentration of mass, thousands of galaxies worth, sitting a couple of 100 million light-years away, and that it, in turn, is being pulled towards something larger still, further along the same current. We will never arrive. The expansion of space is winning at that distance, and the fall has become, in effect, a very slow and permanent leaning. But it's happening right now, underneath everything. You, and the bed, and the house, and the planet, and the sun, and the entire galaxy are falling together towards something we cannot see at 1 million miles an hour, and have been for the whole of your life. Your great-grandparents lived in a universe with one line in the address. Just the Milky Way, and that was assumed to be everything there was. In the space of 4 generations, We've added 4 lines above it, and there is no particular reason to think we've reached the top of the envelope. Rest a moment. All that falling is slow and gentle and already happening without effort. So when we ask where we live, and this is the 5th time tonight I've asked how big the universe really is, the answer now runs to 6 lines. Solar system. Stellar neighborhood. Milky Way, 100,000 light years. Local group, 10 million. Virgo cluster, 54 million. Laniakea, 520 million. 100,000 galaxies, all on the same current. Each line about 100 times the one before it. And that raises the question I've been avoiding all night, the one that ought to have been bothering you since the very first step. How on earth does anyone know any of this? Nobody has been further than the moon. Nobody has flown a tape measure to Andromeda. So where do these numbers actually come from? The answer starts with a woman at a desk in Massachusetts, counting dots on glass plates for 30 cents an hour. Let your body sink softly a little deeper. All that falling is slow and gentle, and you are already being carried quietly along with it. Everything I've told you tonight, the galaxies, the clusters, the millions of light years, nobody knew any of it 100 years ago. That's worth saying plainly, because it's easy to assume this knowledge is ancient. It isn't. Let's start with the simplest measurement, because everything else is built on top of it, and you can do it right now without getting up. Hold your thumb out at arm's length. Close one eye, then the other. Your thumb jumps against the background. That's it. That's the whole idea. The Earth is on one side of its orbit in January, and the other side in July, a baseline of about 186 million miles. Photograph a nearby star in January, photograph it again in July, and it shifts very slightly against the more distant stars behind it. Measure the shift, and simple geometry gives you the distance. The shifts are minute, smaller than the width of a hair seen from across a field. But we can measure them, and a spacecraft called Gaia has now done exactly this for nearly 2 billion stars, patiently, one triangle at a time. So when I said 4.2 light years to Proxima, I didn't mean an estimate. I meant a measurement, taken with the oldest tool in mathematics, from a moving platform, by people being extremely careful. But that trick has a limit. Past a few thousand light years, the shift becomes too small to see, and the thumb stops jumping, which leaves you stuck. And for most of history, that's exactly where astronomy was stuck. Her name was Henrietta Leavitt. She worked at Harvard in the early 1900s in a group of women hired to measure stars on photographic plates. Meticulous work, badly paid, and not considered astronomy at the time. They were called computers, because that's what the word meant then. A person who computes. She was studying a particular kind of star that brightens and dims in a regular rhythm, over days or weeks. And in 1912, she noticed something nobody had seen. The brighter ones pulsed more slowly. The relationship was clean and reliable. Time the rhythm, and you know the star's true brightness. Compare that to how bright it looks from here, and you know how far away it is. Breathe gently. Let the patient quiet of that room settle on you. It sounds modest. It was one of the most important measurements ever made. For the first time, there was a ruler that could reach far beyond the thumb trick, out past our own galaxy entirely, though nobody, including her, quite realized that yet. She wasn't working alone, and it's worth naming the room she was in. There were dozens of them over the years, women hired by Harvard College Observatory to do the measuring and classifying that the men who ran the place considered clerical. They were paid around 25 to 30 cents an hour, less than the unskilled laborers who maintained the building. They were not permitted to operate the telescopes. Their job was to sit with the glass plates the telescopes produced and extract numbers from them, plate after plate, year after year. Between them, that room classified several 100,000 stars. One of them, Annie Jump Cannon, devised the classification scheme for stellar spectra that is still in use today, the sequence every astronomy student on Earth still learns. Another, Antonia Mori, worked out the finer distinctions that later revealed the difference between giant stars and dwarfs. And Leavitt found the ruler that measures the universe. Let your breathing slow. Somewhere, a quiet room full of people counted faint things for years. None of them were called astronomers at the time. They were called computers, and the results were published under the observatory director's name. I'm not telling you this to make a point about fairness, though there is one to make. I'm telling you because it changes the picture of how any of this got known. We tend to imagine a lone genius at an eyepiece on a cold night. The reality was closer to a room full of underpaid women at desks, in daylight, working through glass plates with a magnifier and a notebook, and the size of the universe fell out of the notebooks. At the time, there was an argument going on. A real one, held publicly in Washington in 1920, later called the Great Debate. The question was about the faint spiral smudges visible through telescopes. One side said they were clouds of gas inside our galaxy, because our galaxy was everything. The other side said they were separate galaxies, unthinkably far away. Nobody could settle it because nobody could measure the distance. Then in 1923, an astronomer named Edwin Hubble found one of Leavitt's pulsing stars inside the Andromeda smudge. He timed its rhythm. He applied her relationship. It's worth understanding how that actually works, because it's the cleverest piece of reasoning in this entire evening, and it fits in a paragraph. Imagine you're standing in a field at night, and you can see a light in the distance. You want to know how far away it is. You can't measure the distance directly. All you can measure is how bright it looks. That's not enough. A dim bulb close by and a floodlight far away can look identical from here. But suppose you knew, for certain, that all bulbs of a particular type had exactly the same true brightness. Then looking at how bright one appears would tell you exactly how far away it is, because the only thing that dims a light is distance, and the dimming follows a strict rule. That's what Leavitt found. Her pulsing stars announce their own true brightness by the speed of their rhythm. A slow pulse means a genuinely bright star. A fast pulse means a dimmer one. So find one of those stars anywhere in the sky, time its rhythm, and you know how bright it really is. Compare that against how bright it looks, and the distance falls out. Take a soft breath. Patience is the whole method, and there is no hurry in it anywhere. Astronomers call them standard candles, which is exactly the right name. Leavitt handed the world a set of candles with the wattage printed on the side, scattered conveniently across the universe. And the answer came back, far outside our galaxy. Very far indeed. In one night's measurement, the universe stopped being one galaxy and became a universe. Galaxies. Everything anyone had ever mapped shrank into a single island in an ocean nobody had known was there. Leavitt didn't see most of what followed. She died in 1921, before Hubble made the measurement that used her work, and she was never widely credited in her lifetime. She had been counting dots on glass, carefully, for years, and the dots turned out to contain the size of the universe. I don't tell you that for the sad ending. I tell you for the shape of the work. Almost nothing we've covered tonight was found by dramatic means. It was found by people being patient with faint things for a very long time, usually without knowing what they had. So when we ask how anyone knows any of this, 2 photographs 6 months apart, and a thumb held at arm's length. A woman in Massachusetts noticing that brighter stars pulse more slowly. One man applying her rule to a smudge in 1923 and finding it was another galaxy. That's the whole ladder. Everything above it, the millions of light years, the clusters, the superclusters, rests on those 2 ideas. And there's one more thing that decade discovered, which changes the shape of the entire question we came here with. The galaxies aren't sitting still. They're moving apart. All of them. In every direction. Which means the universe has a beginning, and, as we're about to see, an edge to what we can see of it. Rest here softly a moment. Somewhere, a quiet room of patient people counted faint things slowly, and the counting is gently done, and it turned out well. Within a few years of Hubble's measurement, astronomers looking at many galaxies found something consistent. Their light was stretched, shifted towards the red end of the spectrum, and the further away a galaxy was, the more stretched its light appeared. There's really only one comfortable explanation. They're all moving apart, not flying outward from a center like debris from an explosion. The space between them is growing, everywhere, all at once, the way a loaf of raisin bread rises in an oven, and every raisin moves away from every other one without any of them crawling through the dough. A Belgian priest and physicist named Georges Lemaitre had worked out that this was possible on paper a couple of years earlier from the equations alone. The observations caught up with him. And if everything is spreading apart now, then running the film backwards, everything was closer together before. Closer and hotter and denser, until you arrive at a beginning. That's where the age comes from. 13.8 billion years. Not a guess. It comes from measuring how fast things are separating and asking when they were all in the same place. And it agrees with two completely independent lines of evidence: the ages of the oldest stars and the faint afterglow of the beginning itself. Now the second half, and it's the quiet foundation under everything tonight. Light has a speed limit. Not a limit like a speed limit on a road, which is a rule somebody made and could unmake. It's built into the structure of things. 186,000 miles per second. Not as fast as we've managed so far, as fast as anything can go, ever, by anyone, anywhere. And the strangest part is this. If you were somehow traveling at 99% of that speed, and you measured a passing beam of light, you would not measure it going slightly faster than you. You would measure it going the full amount faster than you, the same figure as someone standing perfectly still. Let your breathing slow softly. Nothing is hurrying anywhere. That doesn't make ordinary sense, and it isn't supposed to. It's simply what every experiment for the last 120 years has found, without a single exception. Space and time adjust themselves to keep that one number fixed. We've known light has a speed at all for longer than most people assume, and the way it was discovered is beautiful. In 1676, a Danish astronomer named Ole Romer was timing the moons of Jupiter. One of them, Io, disappears behind the planet on a very regular schedule, a natural clock ticking away out there, useful for navigation. Except the clock kept losing time. When Earth was on the far side of its orbit from Jupiter, the eclipses ran late. When Earth swung back round to the near side, they caught up again. Romer realized the moon wasn't misbehaving. The light was simply taking longer to reach him when he was further away. breathe out gently. Let the light take as long as it needs to arrive. From a moon going behind a planet, running a few minutes late, he calculated that light took roughly 22 minutes to cross the diameter of Earth's orbit. The modern figure is about 16.5. He was in the right neighborhood 350 years ago, using a telescope you could buy today as an antique. And if that sounds like an abstraction with no bearing on ordinary life, there's a device in your pocket that would stop working without it. Satellite navigation depends on extremely precise timing. Your phone works out where it is by comparing signals from several satellites and measuring the tiny differences in how long each took to arrive. A timing error of 1/1,000,000th of a second becomes a position error of about 300 meters. Those satellites are moving fast, which makes their clocks run slightly slow. They're also higher up in a weaker gravitational field, which makes their clocks run slightly fast. The two effects don't cancel. The second one wins by about 38 millionths of a second per day. Left uncorrected, that would push your position off by roughly 10 kilometers every day. Navigation would be useless within hours. So the correction is built in. Every satellite in the constellation carries a clock deliberately set to tick at the wrong rate on the ground so that it ticks at the right rate once it's up there. Which means the strange physics we've been talking about, time running differently depending on speed and gravity, isn't a curiosity from a textbook. It's a routine engineering adjustment applied every day in a system you use to find a restaurant. The important part isn't the accuracy. It's that light stopped being instantaneous that night. Until then, essentially everyone assumed you saw things as they were, everywhere, always. After that, the sky became a record of the past, and every single distance we've discussed tonight became a length of time as well. Put those two facts together, a finite speed and a finite amount of time since the beginning, and something follows that shapes the entire answer to tonight's question. There is a maximum distance from which anything could possibly have reached us yet. Light from beyond it simply hasn't had time to arrive. Rest here quietly. Nothing about this is urgent, and nothing about it ever was. That boundary is called the observable universe, and it is not a wall. Nothing changes out there. It's a horizon, exactly like the horizon at sea, which moves when you move, and beyond which the ocean carries on perfectly normally, with ships and weather and other people looking at their own horizons. Everyone gets one. Yours is centered on you. Andromeda has its own, offset by 2.5 million light years. Neither of you is at the center of anything. And there's one exception to the speed limit that we'll need in a moment. Nothing can move through space faster than light. But space itself can expand at any rate it likes, and it does. Between very distant galaxies, so much new space is being created that the gap between us grows faster than light could ever cross it. Nothing is breaking the rule. The galaxies aren't racing. The road is being lengthened underneath them. So when we ask why the universe has an edge to it, because light is fast but finite, and time since the beginning is long but finite, and the two together draw a circle around what can possibly have reached us. 13.8 billion years of travel. A horizon, not a wall. One for every observer, centered wherever they happen to be standing. Which finally lets us ask the question properly. We've climbed 15 steps. We have the ruler, we have the method, we have the limit. How big is the observable universe? The answer is not 13.8 billion light years. It's much stranger than that, and the reason why is the last real idea of the night. Breathe out slowly and softly. Let the light take as long as it gently needs. There is no hurry anywhere in any of this, and nothing to chase. Before we take the last step and put a number on all of it, there's a shape to look at. Because when you pull back far enough that entire galaxies become single points of light, the universe stops looking random. It has a structure. Galaxies aren't scattered evenly. They gather along enormous filaments, threads of matter stretching for hundreds of millions of light years. Where filaments cross, clusters form. And between the threads, there are voids, vast, almost perfectly empty regions where there is very nearly nothing at all. Astronomers call it the cosmic web, which is a fair name, though I'd offer you a better one in a moment. Run a sink full of water and add a little soap, then look closely at the foam. You'll see bubbles pressed against bubbles. All the material, all the soap, all the water in the film is stretched thin across the tuics. Surfaces of the bubbles. In the inside of each bubble is nothing. Air. Empty. That's the universe at the largest scale. Matter on the surfaces. Emptiness in the bubbles. And the bubbles are hundreds of millions of light years across. We are living in a film of soap on the side of one of them. The largest single structures anyone has mapped are the walls, where several of those bubbles press together, sheets of galaxies stretching across 1 billion light years or more. One of them, found in a sky survey in 2003, is a wall of galaxies roughly 1 1/3 billion light years long. There is no good way to picture that, so I won't pretend. I'll only note what it means for the shape of things. At the very largest scale, the universe is not a scatter of galaxies. It's a scaffold. And every galaxy is a bead on it. So where are we on it? Not on a wall, as it happens. Not in a void, either. We sit on a modest filament, one of the thinner threads, running between two much larger concentrations. Our local group is a small knot on a minor strand, being drawn slowly along it towards the denser regions we talked about earlier. Which puts us, in the most literal sense available, in the suburbs of the suburbs. A quiet star, 2/3 of the way out in a middling galaxy, in a small group, on a thin thread, at the edge of a supercluster whose boundary is still being argued over. Rest quietly now. Let the soft, empty spaces stay calm. There is a version of that sentence designed to make you feel like nothing. I'd like to offer the other version. Every single thing we have measured tonight was measured from here. From this unremarkable position, on this minor thread, with instruments built by people who could not leave the third rock from a middling star. And it worked. The distances hold. The predictions come true. Send a probe to a moon of Saturn using arithmetic done on Earth, and it arrives, on schedule, years later, at a specific point in space that was empty when you launched. The view from the suburbs turns out to be enough. That's not a small thing to be able to say. It means the universe is comprehensible from an arbitrary spot inside it, that you don't need a privileged position to work out the shape of the whole. Which is, when you think about it, an extraordinarily generous property for a universe to have. It didn't have to be that way. And here's the part that turns this from a picture into evidence. Let your breathing get slower. The shape of everything is already made. We can build that scaffold twice. Once by surveying real galaxies, millions of them, measuring where each one is, and how fast it's receding, and plotting the result. And once inside a computer, by starting with the tiny density ripples visible in that oldest light, applying nothing but gravity and time, and letting 14 billion simulated years run. When you put the two side by side, they match. Same filaments. Same voids. Same knots where the threads cross. That is why anyone believes any of this. Not because the pictures are pretty. Because a simulation that knows only gravity, started from a map of the infant universe, grows into the exact structure we actually see out of the window, and nobody had to tell it to. The voids are the part that stays with me. There's one called the Botis void, found in 1981. It is roughly 330 million light-years across, and it contains almost nothing. A scattering of galaxies float in it, spread so thinly that if our galaxy sat in the middle of it, we would not have known other galaxies existed until about the 1960s. Think about that gently, because it's the most humbling idea of the night, and it isn't about size at all. A civilization could arise inside a void. It could look up at a perfectly ordinary night sky, full of its own local stars, and reasonably conclude that its galaxy was the entire universe. And it would be wrong by a factor of billions, through no fault of its own. No lack of care. No lack of cleverness. Just an unlucky address. We only know better because we happen to live on a bright thread rather than inside a dark bubble. And that thought has a sharper edge to it than it first appears, which I'd like to hand you carefully, because it is the closest thing tonight has to a warning. Everything we know about the universe, we know from a single vantage point. One planet, one galaxy, one position on the web, one narrow slice of time, in a universe that will run for 100 billion years or more. We assume our view is typical. We more or less have to. It's the only view we've got. But the void civilization would assume the same thing, with exactly the same confidence, and be wrong by a factor of billions. Take a calm breath. Let the emptiness out there stay restful rather than lonely. So, the honest version of tonight's answer carries an asterisk. 93 billion light-years is what we can see from here, measured carefully, checked many ways, and almost certainly right about the part we can check. Whether that part is representative of the whole is a question our position simply does not let us answer. I don't say that to undermine any of it. Every number tonight has been earned. I say it because there is a difference between knowing something and knowing the edges of what you know, and the second one is rarer and harder, and is honestly the thing I admire most about the people who worked all this out. They kept writing down where their vision stopped. And there's something else out there holding the whole web together, which we cannot see at all. Galaxies rotate too fast. Far too fast. Given the mass we can actually observe, every star, all the gas, all the dust, they should have flung themselves apart long ago. They haven't. Something is holding them, something with mass and gravity that neither emits nor absorbs light. We call it dark matter, which is really just an honest label for we don't know. And by every measurement we have, there is about 5 times more of it than there is of ordinary matter. Which means everything we have ever seen, every star, every planet, every galaxy, everything that has ever shone or reflected or glowed anywhere in the history of the universe is the minority ingredient. The visible universe is the foam on top of the wave. So when we ask what shape it all has, filaments and voids, like soap film around bubbles, Matter stretched across surfaces, emptiness inside. One void alone, 330 million light-years wide, and nearly empty. And 5/6 of the mass invisible, unidentified, holding the rest in place. Now we have everything we need. The ruler. The method. The limit. The shape. So, how big is the universe, really? Let the quiet settle softly around you. The shape of everything is already gently made. You do not have to hold any of it while you rest. You'd expect the observable universe to be 13.8 billion light-years in radius. Light has traveled for 13.8 billion years, so surely that's how far it's got. But space itself has been expanding the entire time. The distance between things grows while light is still in transit. So the objects whose light is arriving right now have been carried much further away in the meantime. When you account for that, the radius of the observable universe is about 46.5 billion light-years, which makes it roughly 93 billion light-years across. Let's carry the ruler all the way up, one last time, so the number means something. Everything we've climbed tonight, in order. Light crosses the Earth in a 20th of a second. It reaches the moon in a second and a third. It reaches the sun in 8 minutes. It reaches Neptune in 4 hours. It reaches the edge of the Oort Cloud in a year and a half. It reaches the nearest star in 4 years. It crosses our galaxy in 100,000 years. It reaches Andromeda in 2.5 million. It crosses Laniakea in 520 million. And it would need 93 billion years to cross what we can see. Every one of those steps swallowed the one before it. And the last one swallows all of them together many times over without noticing. Inside that volume, there are somewhere in the region of 2 trillion galaxies. Not stars, galaxies. Each holding hundreds of billions of stars of its own. If you tried to count them, one galaxy every second, without rest or sleep, you'd need something like 60,000 years. Not visit. Count. Here's how to hold the idea of the horizon without it feeling like a cage. Stand in thick fog. You can see perhaps 30 feet in every direction, a circle of visible world with you exactly at the center. Walk forward, and the circle walks with you. New things enter at the front. Old things vanish behind. You are not at the center of the fog. You're at the center of your view. of the fog, and so is everyone else, and none of that says anything at all about where the middle is. Every galaxy in that 93 billion light-years has its own sphere, the same size as ours, centered on itself. Ours is not special. It's just ours. And here is the last time delay of the night, the largest one. Breathe slowly. Let it all rest gently where it is. The most distant things we photographed are galaxies, as they were about 13 billion years ago, when the universe was very young. Their light has been traveling almost since the beginning. Those galaxies are not there anymore, not like that. They grew, merged, aged, changed completely. What we see is a portrait of infancy, delivered 13 billion years late. The deepest images ever taken are not photographs of the distant universe. They're photographs of the distant past. Every telescope is a time machine, and they only point one way, which leads to something that sounds like a paradox and isn't. There are galaxies whose light is arriving tonight that are now more than 30 billion light-years away, further than the age of the universe would seem to allow. The light left when they were much closer. Space stretched underneath it while it traveled. By the time it got here, the source had been carried far beyond the distance the journey took. So the photograph and the object are in two different places, and both are real. And there is a story hidden in the depth of those images that I think is the single most extraordinary thing in modern astronomy. Breathe slowly here. That is the top of the stairs, and there is nothing further to climb. When telescopes look far enough back, they find galaxies already assembled just a few 100 million years after the beginning, much earlier than anyone expected, and larger than the models comfortably allowed. Bright, structured things existing when the universe was less than 3% of its current age. Nobody is quite sure yet how they got so big so fast. The models are being adjusted. Arguments are ongoing, in journals, right now, while you're lying there. I mention that deliberately because it would be easy to give you tonight as a finished picture, a tidy staircase with a number at the top. It isn't finished. The top few steps are still being rebuilt while we stand on them, and the people rebuilding them do not agree with each other yet. That's not a weakness in the answer. It's what a living answer looks like. There's one more number at this altitude, and it's the one that most deserves the word enormous. We've been talking about how far we can see. But we should also ask how far we can ever reach, and those are very different distances. Because space is expanding, and the expansion is accelerating, most of what we can currently see is already permanently out of reach. Not far away. Unreachable. A signal sent tonight at the speed of light would never arrive, because the space in between is growing faster than the signal can cross it. The region we could still theoretically send something to, the part of the universe we could ever interact with, even in principle, even given infinite time, is a sphere of about 16 billion light-years in radius. Compare that against the 46.5 billion we can see, and the arithmetic is stark. Somewhere around 95% of the galaxies currently visible in our sky are already beyond any possible contact. We can watch them. We can measure them. We will never touch them, and nothing we do will ever affect them in any way. They are, in the most complete sense, a view rather than a place. And I want to hand that to you gently, because it sounds like loss and I don't think it is. Everything on this staircase tonight, every step from the ground beneath you to the horizon of the oldest light, is something we were never going to visit. Not the Oort Cloud. Not Proxima. Certainly not Andromeda. The reaching was never on offer. What was on offer was the looking. And the looking turned out to be enough to build the whole map. We are a species that worked out the size and age of the universe from inside a single room and will never leave the room, and did it anyway. That's not a limitation you have to feel sad about at this hour. It's closer to the best thing about us. And past those first galaxies, there is one more thing to see, and then nothing. A faint glow fills the entire sky in every direction, the leftover heat of the early universe, released about 380,000 years after the beginning, when things cooled just enough for light to travel freely for the first time. It is the oldest light there is. Nothing older can ever be seen, because before that moment, the universe was not transparent. Let your body settle completely. The counting is finished now. That glow is arriving at you right now, from every direction at once, passing through the room you're lying in. Very faint, very cold, but genuinely here, an unbroken signal from the beginning of everything, still going, landing on your roof tonight. It has a temperature, and it's about 2.7 degrees above absolute zero. That's what's left of a fire that once filled all of space. The whole universe has cooled to just under 3 degrees above the coldest anything can be. And it was found by accident, which is my favorite part. In 1964, 2 engineers in New Jersey were testing a large horn-shaped antenna and could not get rid of a faint hiss. They checked everything. They cooled the receiver. They eliminated the city, the sky, the equipment. They found pigeons nesting inside the horn, evicted them, and scrubbed out what one of them politely called a white dielectric material. The hiss remained. Same in every direction, day and night, all year. It was the afterglow of the beginning, and they had been trying to clean it off. There's a domestic version of that, if you're old enough to have had a television with an aerial. When you tune to a channel with no station, a small fraction of that static, the snow on the screen, the hiss from the speaker, was this. The oldest light in the universe, arriving in a living room, mistaken for a fault. That is the wall, not the edge of the universe. The edge of what light can tell us. So when we ask how big the universe really is, here is the honest answer to the half we can measure. 93 billion light-years across. 2 trillion galaxies. 13.8 billion years old. A horizon drawn by the speed of light, centered on you, exactly as it is centered on everyone. That's the top of the staircase. The rest of tonight isn't a climb. We're going to sit at the top for a while, look at what lies past the horizon, and then walk all the way home. Let your breathing slow right down now, softly. That is the quiet top of the stairs. There is nothing further to climb tonight, and nothing left to carry. So how big is the universe, really? We can answer half the question with confidence, and we just did. What we can see is about 93 billion light-years across, holds around 2 trillion galaxies, and is 13.8 billion years old. The other half is harder, and I'd rather be honest with you than tidy. We don't know how big the whole universe is. We may never know. Because nothing beyond that horizon has had time to send us anything. No light, no signal, nothing that could be observed directly, however long we wait, or however good the instruments become. But not being able to see a thing is not quite the same as knowing nothing about it. And we're not entirely without hints. We can measure the shape of space itself, whether it curves like the surface of a ball, or bends the other way, or lies flat. We do it by looking at that oldest light and measuring very precisely how large its patterns appear. The answer, as far as we can measure, is flat. Flat to within a very small margin. And in the simplest picture, a universe that is flat everywhere would be infinite. That's a real possibility, taken seriously. Not very big, infinite. Going on without end in every direction, with galaxies in all of it. Though flatness alone doesn't settle it. Space could in principle be flat, and still close on itself far away, the way a very long strip of paper is flat everywhere, and yet joins its own beginning if you walk far enough. and people have looked for that, which I find rather wonderful. If space closed on itself at a scale we could see across, light would come round the loop, and the same patch of that oldest light would appear twice in the sky, in two different directions, matching circles, like seeing the back of your own head at the far end of a corridor of mirrors. Astronomers searched the sky for those matching circles. They didn't find any, which doesn't prove space goes on forever. It only means that if it does close on itself, it does so on a scale larger than everything we can see. So the honest position, and a restful one, is that the universe is either endless or so large that the difference never quietly reaches us. Let your body soften. Rest quietly with that thought. Even the cautious estimates, the ones assuming space might curve very slightly, too slightly for us to detect, put the whole universe at hundreds of times wider than the part we can see. Some analyses suggest at least 250 times across, which would make the volume beyond our horizon more than 15 million times the volume inside it. 93 billion light-years is the small, well-lit room we happen to be standing in. The house may have no walls, and it's still growing. Space is expanding everywhere, all the time, and the expansion is speeding up. Distant galaxies drift further from us each year, and the further away they are, the faster they recede. Far enough out, that recession exceeds the speed of light, not because anything is moving through space too quickly, but because space itself is stretching between us. Those galaxies are already beyond any possible contact. Their light is on its way, and it is losing. Which means the sky is very slowly emptying. Let your breathing slow right down. Nothing left tonight is a fact you need to hold. In the far future, 100 billion years or so, galaxies now visible will have crossed beyond the horizon, one by one, quietly, without any event to mark it. Astronomers of that era, if there are any, will look out and see only their own local group of stars, floating in what appears to be an infinite and permanent dark. They will have no way to know about any of this. No other galaxies to observe. No redshift to measure. And the afterglow of the beginning will still be there, technically, but stretched to wavelengths so long and so faint that nothing they could reasonably build would ever catch it. They will do good science, carefully, and conclude that the universe is small, static, and eternal, and they will be wrong, and there will be no evidence anywhere in their sky to correct them. Which means something rather remarkable about right now. We are living during the era when the universe is still legible. The light is still arriving. The evidence is still in the sky. For a window of time, a wide window, but a window, it is possible for something inside the universe to look out and work out what the universe is. You happen to be alive during that window. So am I. Out of all the eras there will ever be, we got one of the ones where you can still find out. That is not nothing. I'd say it's the luckiest thing in this whole 3 hours. Now, I've spent 3 hours giving you numbers, and I'd like to spend the last of our time taking them back off you, because they were never the point. There's a feeling that tends to arrive somewhere around here, and it usually arrives disguised as a thought. It goes something like, if all of that is true, then nothing I do matters. I'd like to sit with that for a moment, rather than rush past it, because it deserves better than a slogan. Here's what I've come to think, for whatever it's worth at this hour. Scale is not the measure of meaning. It never was. The universe is not a competition for importance that you lose by being small. A galaxy is not more meaningful than a kitchen table because it is wider. Size is a fact about extent, and meaning is a fact about relationship, and those are two different kinds of thing entirely, measured with different instruments. Rest here softly. Let the meaning arrive on its own, without any effort from you. Nothing we cross tonight cares about you. That's true. But nothing we cross tonight is capable of caring about anything. The caring is all down here, in the thin film of air, on the small, warm world, among the people who happen to be doing it. That isn't a consolation prize. As far as we can tell, it's the rarest thing in the entire 93 billion light years. And there's one more thing, and then I'll stop with the ideas altogether. Every heavy atom in your body, the iron in your blood, the calcium in your bones, the oxygen you're breathing in right now, was made inside a star. Not as a metaphor. Literally. Those atoms were forged inside stars that lived and died long before the Earth existed, and were scattered outward when those stars came to their ends, some drifting gently away on slow stellar winds over thousands of years, some thrown out in the explosions that end the largest stars, and some, like much of the iron, released when an old dead star finally detonated. Which means the universe we spent tonight measuring is not a place you're looking at from outside. It's a place you're made of. You are small. But you are not separate. You are brief. But you are part of something that has been going for 13.8 billion years and shows no sign at all of stopping. That's what I'd like you to take into sleep. Not the numbers. That. And now, let's go home. All the way back, slowly, in reverse, and let it get smaller and warmer with every step. Let your breathing slow now. There's nothing left to learn tonight. We're going to walk the whole way home, and you don't have to follow any of it. Let the names go past, like stations on a train you're already asleep on. Back in from the horizon of the oldest light. In through the 2 trillion galaxies, each one turning slowly, none of them in any hurry. Past the great voids, and the long, bright filaments, and the soap film shape of everything. Back through Laniakea, 520 million light-years of slow current, carrying us gently, the way it has since, long before there was anyone here to notice. Past the far edge of the Virgo cluster, that great city we never lived in. Into our own quiet local group. Past Andromeda, that faint oval smudge still falling towards us, 4 billion years from arriving, in no rush whatsoever. Into our own galaxy now. Down through the spiral arms. Past 100 billion stars, each one a sun, most of them with worlds of their own, turning quietly in the dark. 26,000 light-years inward, to one ordinary yellow star in a quiet suburb, 20 laps into its long, slow orbit. Past the Oort Cloud, a 1.5 years of light in every direction, all of it dark, all of it patient. Past the comets, waiting out there on their long, slow paths, some of them not due back for 1,000 years. Past Voyager, still going, still carrying the sound of rain on a shore. Past Neptune, 4 hours of light out, where the sun is only the brightest star in a very dark sky. Past Jupiter and its slow-turning storms. Past Mars, to a small blue world, 93 million miles from its star. 8 minutes of warmth on the daylight side. Wrapped in a skin of air 10 miles deep, thinner than the skin of an apple, holding everything that has ever lived. Down through that air now. Through the weather. Through whatever clouds are over your part of the world tonight. Down to a building. To a room. To a bed. To you, lying there, still being carried at 1,000 miles an hour by the turning of the world and not feeling a thing. Everything we cross tonight is real, and all of it is still out there, exactly as it was, whether anyone is awake to think about it or not. Let your breathing be slow and easy now, the way it goes just before sleep. And none of it needs anything from you right now. There's nothing out there you have to hold up. Nothing you have to keep track of. It managed for 13.8 billion years before you arrived, and it will manage perfectly well tonight while you sleep. So let it get on with it. Let your breathing slow. Let your body get heavier against the bed. Let the numbers go. They were never the point, and you're allowed to forget every one of them. Above the roof, all that quiet light is still arriving. From the moon, a second and a half away. From the sun, 8 minutes back. From stars whose light set out before anyone alive was born. It's landing on the tiles right now, and on the road outside, and on the backs of your closed eyelids, and nobody notices because it's far too faint to feel. It has been doing that every night of your life. The light of one star. The light of 100 billion stars turning in one slow wheel. The light of 2 trillion galaxies drifting quietly apart in the dark. And underneath all of it, one small warm room with you in it, breathing slowly. Let everything soften. You are nearly home, and there is nothing left to do. Think of it this way, if any thinking is still happening. Every step we took tonight was outward, and every step made the last one look small. But the direction was never really the point. We could have gone the other way, down into the grain of sand, into the atom, into whatever is under that, and the staircase would have gone just as far, and each step would have made the last one look enormous. You are standing where those 2 staircases meet. Not at the center of anything. At the join. And the join is the only place in either direction where anyone is counting. The universe is not more real for being large. A galaxy is not more true than a room. All that size out there does exactly what size does, which is take up space, while the small warm things down here go on doing the only thing that has ever seemed to matter, which is noticing and caring and getting some sleep. You are a small, warm room in a very large night. That has always been true. And it has always been enough. Thank you for spending this time with me tonight. You're welcome to come back to this whenever you need it. Start it again from the beginning, as many nights as you like. It will always be here, and it will always take the same slow way round. And if it helped you rest, subscribing means the next quiet journey finds you without you having to go looking for it, and it helps someone else who's lying awake tonight find their way here too. May your night be peaceful. May your thoughts be light. And may sleep come easily, carrying you gently into morning. Good night.